Welcome to the lecture on fundamentals of MIMO wireless communications. We are currently studying the propagation model, the small scale fading. What we have seen is the characteristics of flat fading, and what we have found is that the received signal when a continuous wave is sent is random. The amplitude of the signal fluctuates over time, and the fluctuation is a random process. To describe it, we have seen the distribution of the signal. We have seen the distribution of the envelope, the distribution of the envelope squared, and also we have studied the correlation properties, where we have seen the correlation of the received signal, we have seen the correlation of the envelope, and we have also seen the correlation of envelope squared. And summarily, for the Rayleigh fading condition, that means where arrival angles are uniformly distributed, we have seen that the correlation is proportional to Bessel function of the 0th order of the first kind, and that of the envelope and envelope squared both are proportional to that of J0 squared instead of J0. So with that, we have summarily covered the random signal. So to characterize it, we have looked at the distribution of the signal, of the envelope squared. We have also looked at the correlation of the signal through phi HH delta t. We have looked at that of the envelope. For one case, we have found it to be J0 2 pi Fm delta t for envelope, and for envelope squared we found it to be J0 squared of the same term. And why this envelope and envelope squared are important, because this will be the amplitude and this will be the power of the received signal, and the signal is important because when we will be doing baseband processing, this is what we will be handling. So therefore these are all important. Now along with these, to characterize the signals or to design better communication systems, we also look at two important parameters. One is the level crossing rate, and the other is the average duration of fade. So with this characterization, we would be fairly well characterizing the received signal for the particular case that we are considering. The level crossing rate is often defined as the rate at which the signal crosses a particular threshold. So that is, if we are taking the signal fluctuation, that means if this is the time axis, and as we have said, the signal fluctuates randomly. Of course, we are assuming some inherent Fm value in this. So if we set some level, let this level be a level which is corresponding to the receiver performance. So if this is the level for receiver performance, the rate at which it crosses this threshold in one direction, that means either from above to below. So here it is crossing, there it is no crossing, here it is crossing, there it is crossing, there it is crossing, there it is crossing, it is crossing in one direction, or there it is crossing, there it is crossing, or we take the rate at which it crosses in the upward direction, either the first one or the second one. We do not take both. So either the first one or the second one, and we define it as the number of crossings per unit time, that means per second. So rate at which it crosses a particular threshold. We could have multiple thresholds. So this is the basic definition. Now why this is important? This is important because we would like to know at what rate the signal goes below the threshold, that means what is the rate of outage. So usually outage can be calculated from this, and the average duration of fade is basically if this is the desired level and this is the period for which the signal has remained below the threshold, that means it has gone down and then it has come up. So what we are interested in calculating, what is the average period for which the signal goes below the threshold. Now, both would indicate our calculations on outage, because once it goes below the threshold, it will remain below a threshold for a long duration, or the duration corresponding to the average duration of fade. So, here again the discussion that we were having, that if we consider another situation where the signal is fluctuating very slowly, this we had said earlier. So, as we can see that the slow fading gives us advantage, that the rate of change of signal is slow compared to the symbol duration. Suppose this is the symbol duration, it is slow compared to symbol duration, but once it goes below a threshold, it remains below a threshold for a long duration of time. That is the disadvantage. Okay. Whereas, if you look at the other one, the rate of crossing is faster. So, the two has their own advantage and disadvantage. In this case, the signal might be fluctuating within the symbol duration, but since it is fluctuating faster, it will not remain below a threshold for a long time. On the other hand, it goes below the threshold several times. So, if we can understand this process, or if we can know what are the details of this, then we could design communication systems accordingly, and this influences the error correction code design more often. The forward error correction codes, the interleaver design, these are some of the important things which interleaver design, which affects the communication systems for these particular modules. So, we will just briefly look at how these metrics are defined, and then we will proceed with it. So, level crossing rate is basically talking about how often a signal crosses a particular threshold, as defined by the level crossing rate, and as we have just said, the envelope level crossing rate is what is important. So, at a specified level r, which we have drawn in the paper, LR is defined as the rate at which the signal envelope crosses the level R in positive or negative going direction. This is what we described. So, that means if this is the fluctuation, so either you count the rate at which crosses this direction, or you count the other direction, Okay. And the actual calculation is something which requires the joint distribution of the envelope as well as that of the rate of change of envelope. So, basically we have alpha of t and alpha dot of t, that means the derivative of alpha with respect to t, and that is required because it gives us the rate at which the signal is changing. So, the rate is calculated by alpha dot of t. We are not going to do the details of the derivation of this particular expression. We will be interested in the expression for this particular course. So, the level is defined with respect to the RMS value. So, if R is our level of interest, we define rho, which is with respect to square root of the total received power. So, that is root over omega p, and that is the definition of R. And for Rayleigh fading condition, which is of our interest, that is isotropic scattering, 2D isotropic scattering model, the derivation would give a result which is the rate at which crosses the threshold is equal to square root 2 pi. So, there is a constant. What is important is Fm times rho e to the power of minus rho squared. So, if we concentrate on some of the important terms, the most important term as of now would be Fm. So, what is clearly from this particular formula is Lr, the rate at which it crosses a threshold, is proportional to Fm, and Fm is equal to V by C times Fc. So, clearly again, as Doppler frequency increases, which is because of either velocity or of carrier frequency, the rate at which it crosses the threshold increases, and we have seen this through the drawings in the paper. So, that is what is the level crossing rate. This is one of the important measures of the channel behavior. Accordingly, things get designed. Moving ahead further, the average duration of fade is another important quantity which is often used. So, the average duration of fade is defined as the average duration. This is very important. It is the average duration, not the exact duration. The envelope remains below a specific level. This is what I have already described in this figure, that what is the time duration for which it remains below this threshold. So, it is talking about this duration. It is talking about this particular duration, that it remains below the threshold in this case and this cases. So, what we are interested is in the average duration that it remains below the threshold. Now, to do this calculation, what is done is we first calculate the probability of the envelope remaining below R. If you look at it, that is probability that the envelope is remaining below some level R divided by the rate at which it crosses that level in one particular direction, let us say in one direction. So, that will give us on an average how long it is going to remain below the threshold. Now, probability that the envelope is below a threshold is given by this expression. If you take Rayleigh distribution and you integrate this, you are going to get 1 minus e to the power of minus rho squared, and the average duration of fade would be this probability, this is the expression, divided by the rate at which it crosses. So, if you would take the LCR calculated in the previous page and divide this divided by this, you are going to end up in the expression which is the average duration of fade. So, together using these two quantities, often some of the important modules of a digital communication system are designed. So, at this point we will stop our discussion on small scale fading and flat fading. So, what we have essentially discussed is all these things as is here for flat fading. And we have also discussed time selective fading, that means slow fading or fast fading. So, when we have fading, we had said there is time selectivity, there is frequency selectivity, there is space selectivity. For time selective, there could be slow or fast, there could be for frequency, it could be flat or frequency selective, for space also. So, we have studied the slow fading when we said that coherence time is much larger than the symbol duration, and fast fading when coherence time is smaller than the symbol duration. Flat fading we have already seen when the signal is flat across the bandwidth of interest, and that happens when all the taus, the delays because of multipath, these multipath effects that we had drawn, they are all on the ellipse for which the two focal points are the transmitter and the receiver. So, that means they are having almost the same delay. So, all the reflected paths arrive almost at the same delay. So, the impulse response is basically an impulse. In that case, the response is flat across frequency. So, across the frequency axis, the response is flat. We have seen that, and what we will now proceed to see is frequency selective fading. So, when we look at frequency selective fading, we will concentrate first on the so, we will take a look at this particular picture. We will not take a look at this picture as of now. So, let us assume the transmitter is located here, the receiver is located at this point, and there are rays which are going from the transmitter to the receiver. These are rays which are going from the transmitter to receiver. Now, for these two rays that we have drawn, since they are get on the same ellipse, they are getting reflected from the same ellipse, their path delays would be the same. So, if there were rays coming from this and this, they would be multipath as we have studied before, but since they are getting reflected from the same ellipse or reflectors on the same ellipse, what would we have is on the delay axis, the echoes would appear at the same point, they will not be different. So, we will be getting flat fading, because if you take the Fourier transform across the delay axis h of t comma tau, you are going to get a flat response across the frequency. This is what we are going to get. Now, instead we relax the assumption and we say that the signal propagates, gets reflected, this also gets reflected. However, there are rays or waves which get reflected from reflectors or scatterers which are further away. That means, the propagation delay is not the same. While deriving the flat fading, we had made the assumption let tau 1 is almost equal to tau 2 is almost equal to tau n finally, and that finally getting equal to tau capital N, right. So, this is the assumption that we made, and this was set equal to tau cap, and then we had h of t comma tau is equal to h of t times delta tau minus tau cap. This is what we have had. So, now in this case we do not make these assumptions, we say they are not equal to tau cap, they are all different, they are distinguishable. So, that is what is represented by this particular picture. So, that means this ellipse is the one where the delay is tau 1, the second ellipse is the one which represents a delay of tau 2. That means, a wave propagating from here getting reflected coming over here would have a delay of tau 2, and the one getting reflected on the third and coming back would have a delay of tau 3, and so on. So, these are basically resolvable delays, the delays which the receiver can distinguish. For instance, if the receiver has a symbol duration which is 1 millisecond, it will not be able to distinguish between the paths which are coming within 1 millisecond. So, these will be relative to the particular receiver. Of course, we will take a better look at it. So, now we will try to we will try to draw it here. Suppose I launch an impulse. Suppose I have launched an impulse, and that impulse propagates through the air, and it comes to the receiver after multiple reflections. So, if I draw the delay axis, so after some propagation delay which is tau 0, I have launched an impulse, I am going to get the echo at a certain delay, what we have seen. In case of flat fading, the other echoes would also be on top of this, and there will be n number of such echoes. This is going to happen in this case. Now, when the second set of delays is coming from a reflector which is on the second ellipse. So, that means this is a transmitter receiver, this is on the first ellipse, there is a whole set of reflectors on the second ellipse, let us say, they will come with a delay of tau 2. So, if this is tau 1, they will come from the reflectors at tau 2, one path, second path, third path, and so on. So, they are all going to come and be on top of each other. This delay is tau 2. If there are reflectors further away or scatterers, they are going to get reflected, hit and come back to this. So, then there again there would be reflections, and this delay is tau 3, right. So, what we see is that the delta what we have here what we have is h being the coefficient which is function of time, as we have seen, because when this is not considered, we have seen this h of t, and the delay was tau 1 for all of them. We had basically written h of t comma tau is equal to h t times delta t minus tau cap, and that is tau 1. For the second one, we have h of t comma tau 2, and so on, h of t comma tau 3. So, all these are function of time, but they are at different delays, right. So, what we have h t comma tau is basically sum of, we have L equals 1 to capital L, let us say, and h of, or we have to change the index, t comma tau L delta tau minus tau L. This is because h at the delay tau L, and that is being specified by delta tau minus tau L. This could also be written as h l t 1 delta tau minus tau L. That means, this is at a delay of tau L. What we should remember is there is an additional summation n equals to 1 to n h n. That means, at the delay tau L, there are n number of multipaths. That means, there are n number of multipaths. So, I draw the figure again. So, if there is the first ellipse, path number 1, path number 2, path number 3, path number small n, up to path number capital N. In the second ellipse, now all of these are at a delay of tau 1, that is what we have. The second ellipse, there would again be a large number of them. So, ideally speaking, what we should have is sum over n suffix l, indicating the number of paths multipaths at lth delay. So, that is what should indicate, that means the number of reflectors on the second delay is not necessarily equal to the number of paths in the first delay and that with the third delay. So, this number n would vary according to the delays. So, what we have is this is one of the echoes, this is the second echoes, this is the third echoes, and with time, if I draw time on this axis, and would track this, what we would find is h is a function of t that we have already seen. So, this is going to fluctuate with time. What we have seen is the distribution of this. We have seen the distribution to be Rayleigh distributed, the envelope to be Rayleigh distributed, and the received signal is complex Gaussian distributed. The envelope is exponential distributed for p theta equals to 1 by 2 pi. So, what we have studied is basically one of the paths. What we have studied is what could happen in the second delay, what could happen in the third delay. This is what we have already studied. Now, what we have is whatever we have studied for one delay is getting replicated in the second, the third, the fourth, and so on, and they are staggered in the delay axis. So, all are fluctuating. This is very important to remember. So, all that we have studied till now, the properties, that means whatever we have mentioned here, the random distribution of the signal, envelope, ML squared, the correlation, the Doppler spectrum, we have also studied the Doppler spectrum, is everything for this path, because this path is made up of several multipaths coming at that delay. This is another group of multipaths coming at a second delay. This is another group of multipaths coming at another delay. We have studied this axis. In this axis, we have studied the correlation. In this axis, we have studied the Doppler. So, we have taken the Fourier transform across the time axis, and what we have reached is the Jake spectrum. And we have also studied specular component in this case, where there would be Rician. We have talked about the distribution to be Nakagami on this. So, if I cover up everything else, whatever we have studied is this particular one. So, another easy way of drawing this matching with what we have done before is, if this is our axis of time, let us say I have reversed the time axis. Previously, in the previous picture, this was h of tau. So, the received signal for continuous wave transmission, we saw it to be fluctuating like this with time. Now, if I would draw tau on this axis, now I have rotated the axis. So, this could be at some delay tau 1, at another delay tau 2, we would find same thing happening. At another delay tau 3, we would find this happening. So, whatever we have studied for this, the PDF, the h delta t would apply for these also, and the PDF would apply, this would be phi h h. Now, instead of just putting delta t, we would put at tau 2 in this case. This was at tau 1. So, whatever we have studied for the delay tau 1, this would be phi h h delta t for delay tau 3 and so on. This is what we have actually studied, the PDF and all. So, one question that can arise in our mind is the correlation property the same across all of this, and if the PDF would be same across all of this. Now, that is not necessarily true that it is going to be the same for all of them. Some of them could be Rayleigh, some of them could be Rician, and wherever there is Rician, there would be according distribution of the Doppler and the correlation function. So, there could be a mixture model of all of these which could apply in each of the delays. Typically, we would prefer to have the diagram as in this, that means here we have made this as the time axis, this as the delay axis, and usually we would prefer to describe it in terms of power delay profile, because there is a certain kind of profiling that happens in this delay axis. This is the delay axis, this is the h of d comma tau axis. Okay. So, typically the reflectors which are close by, the propagation path is smaller compared to propagation path on the second ellipse or the third ellipse. We would expect signals from the first tier of reflectors to be stronger than the one from the second and the third because of dissipation, but that is not necessarily true for instantaneous cases. On an average, that could be true, and we would describe these in terms of power delay profile, which we will describe shortly. So, what we have with us is in this particular picture. Now, we concentrate on the second picture, which is showing us the power delay profile, and there to understand it, we could say that we have launched an impulse at some point here. We have launched an experimental impulse, and because of the impulse we are getting first echo here. That means all multipaths coming at that delay. This is contributing to multipaths from the second delay, second group delay. Now, in this picture I have changed from what I have drawn in on the paper over here. Here we had said that the first delay is having stronger signal than the second and the third and so forth. So, it could be the other way also. The first one is having a lot of absorbing material where it gets reflected from, whereas the second tier, that means this particular one, could be having a lot of metals. So, there could be specular components, there will be strong reflections from them. So, that is what we have drawn here, and this is the third group of reflectors. So, you can say this is the tau 3, this is the tau 1, this is the tau 2, this is the tau 1 corresponding to the ellipses here, and so on. So, these echoes will keep coming till the time we are able to resolve them. So, in order to resolve them or in order to record them, we usually set the noise floor or the sensitivity level of the receiver. Once the echoes fall below the sensitivity of the receiver, we no longer are able to record them, and till that point, from the first point of occurrence of the signal to the last point of the occurrence of the signal is what is important for us, and we usually refer that as maximum excess delay. This, as you can clearly see, it is from this point to this point, because this has gone below the threshold. From this point to this point, that is called the maximum excess delay. Why it is called excess delay? Because what we are interested is in the initial delay is due to propagation, and that is common for all. If you look at it, this section is common for all. So, basically there is a tau 0 and or a tau 1 at this point, tau 2, tau 3. So, we are interested from the first point that it occurs is when the signal comes for the first time. Now, if there is no further delay, these will not be present, this section will not be present. That means, this section is not present, this section is not present, this section is not present. So, basically if there was flat fading, only the first one would be present, nothing would be present. Now, beyond that condition, we are at a situation where there is an excess amount of delay over here, there is an additional amount of delay, there is an additional amount of delay. So, these delays are therefore called excess delay, and this duration from the first to the last recorded value is the maximum delay, and this is the excess with respect to the first one, and hence it is called the maximum excess delay. So, we stop our discussion at this point. In the next lecture, we will go into the details of this particular model and how this particular model helps us in characterizing the received signal, and what we will be able to understand is what is known as frequency selective fading. That will bring us to the end of understanding small scale propagation effects, which is necessary for this particular course. Thank you.